All right, in this presentation, we're going to talk about Kirchhoff's rules. Kirchhoff's rules deal with electrical circuits as a whole. So we're looking at circuit configuration and how those configurations affect the three main types of quantities inside a circuit: voltage, current, and resistance. Okay, so we're just going to start with our rules here. And so the first rule is Kirchhoff's loop rule. And this states that the sum of voltages across electrical devices in a circuit when following a loop from a point in the circuit equals zero. So we're going to sum up, or we're going to add voltages across electrical devices in a circuit. And we're going to use that to follow this rule. Now, the first thing you have to do is you have to pick where you want to start your loop at. Now, in this circuit, I see more than one loop. I see this loop where I start here at this device, and I go this direction. Okay, then we'll call that loop 1. I see a second loop that goes all the way around the outside, and there's no real reason to go a certain way around the circuit. I just like to do it in a clockwise manner just because it's easier, and we'll call this loop 2. But I also have this other loop, and we'll call it, we can start here and we call this loop. And just so I can show you that it doesn't really matter what direction we go, I'm going to make this loop 3 go in the opposite direction. Now, when we do Kirchhoff's loop rule, we have to start a convention of labeling our resistors positive and negative, and what side is positive and negative. So our battery is already simple. It's the long side is the positive side, the short side is the negative side. Now on our resistors, anything that is closest electrically to the positive side of the battery gets a positive sign. So this side of my resistor is closest to the positive side of the battery electrically, which means through this wire, than this side. In other words, to get to that positive side, I have to go up and through the resistor, so it gets a negative sign. Now on this resistor, this side of the top side of my resistor is close electrically to the positive side than the bottom of my resistor. So once again, a positive and a negative, and then over here, positive and negative following that same rule. Now the reason why we do this is because when we go to sum up our voltages, we need to take the sign of the leaving sign, the exit sign. Okay, so I start on my first loop. Now we're going to start talking on our loop. So this is going to be loop 1. All right, loop 1. And if I were to follow the voltages, well, here I have the voltage total, the total voltage from the battery. And we'll call this V1, we'll call this V2, and we'll call this V3. Okay, so if I look at loop 1, well, I start here. And remember, the rule is take the sign leaving, the leaving sign. So I go over here and I go across my battery, and the leaving sign is positive. And so that means that I'm going to have a positive total voltage. Right? And then I'm going to add to that, because it's the sum, the next one. So I come over here and I follow my loop, and I come back down here, and the leaving sign here is negative. And so it's going to be minus V1, right? And then I'm going to continue going down. So let's add, this is the sum. And I come down here to V2, and so the voltage across the second resistor, and then the leaving sign is also negative, so minus V2. And that continues, and that finishes up my loop. So once I'm back here at the end, I say equals 0. Now I can rearrange this, and let's make everything positive. And the way that I'm going to do this, I'm going to add V1 and add V2 to the other side. So I get my total voltage equals V1 plus V2. Good. So there's loop 1. Let's look at loop 2. Now loop 2 goes all the way around the outside. So we're going to start at the same point, and we're going to loop our way all the way around. Now the total voltage here, well, I'm going to add that. So once again, positive V total. Then I'm going to add the next one. And if I follow loop 2, well, I go down this other branch, and I take the sign of leaving, which is negative, minus V3. which is the voltage across this third resistor. And then I follow my loop back around to the beginning, and I'm back to the beginning, so that's going to equal 0. And now if I were to rearrange this so that I have all positive, my total voltage equals the voltage across resistor 3. Okay, good. Now let's work out loop 3. All right? And so loop 3, we're going to start down here at this corner. Now loop 3 says that I'm going to go across here, and I'm going to get positive V3 because I'm going in this direction, right? And so the sign of leaving in this case is positive. So positive V3. And then now I'm going to come back down this branch, and I go through resistor 1, or voltage across resistor 1. Then I take the sign of leaving, so minus V1. And then I take the sign of leaving of voltage across resistor 2, V2, so minus V2. And then I follow that back around, and I hit my starting point, so that's going to equal 0. Now, if I were to rearrange this, then I get V3 equals V1 plus V2. And if I look here, V1 plus V2 equals my total voltage, and my total voltage equals V3. Well, then that means that V3 equals V1 plus V2. Okay, so Kirchhoff's loop rule works out mathematically. Now, we need to look at, well, what does this mean for our circuit and the voltages? Okay, well, let's see here. If I have objects in series, which is the resistor 1 and resistor 2, well, then my voltages add up to be my total voltage. So if I have a series circuit, so series, in series, my total voltage, or the voltage across the battery, equals the sum of all my other volts, so all my other voltages across the resistor. So V1 plus V2 plus V3 plus ... all of my voltages that are in series. You see that? Okay, now parallel has its, let's make parallel, not rel, parallel. Okay, there we go. All right, now this resistor 3 is in parallel with my battery, right? Because they're connected in that way. And so if I were to look here, well, I said that the voltage, total voltage, equals voltage across resistor 3. So in parallel, the total voltage equals the voltage across resistor 3. If I had any other voltages, if I had a resistor inside my circuit, it would be that. But anyways, in a parallel circuit, my voltages equal each other. And so this, don't get this confused. And let me go ahead and highlight that just so that we know what I'm saying. This is not this resistor 3. This would be if I had 3 resistors in series. So that means that if I had another resistor right here. All right? So keep that in mind. Also, this V1 and V2 would be if I had another resistor in parallel. So these are completely hypothetical. They do not fall in with this circuit exactly. But just know that in a parallel circuit, if they're in parallel, their voltages are equal to each other. In a series circuit, if they're in series, their voltages add up to be the voltages of the battery. Okay, now let's talk about Kirchhoff's junction rule. Kirchhoff's junction rule states that the sum of electrical current flowing into a junction equals the sum of the electrical current flowing out of the junction. And you can kind of get the idea of this if you were to think about water current. All right, so if I were to identify my junctions here, well, there's a junction and there's a junction. And I were to say that I have 5 gallons that flow in of water. So if this was a hose, 5 gallons flow in. Well, I better have 5 gallons coming back out, otherwise I'm losing water somewhere. But and so we can see that the same thing should be true for electrical current. So instead of 5 gallons, if I have 5 amps coming in, well, then I should have 5 amps coming out of that junction. And then likewise here, if I have 5 amps and some of it comes down this branch and some of it come down to this branch, and then when they recombine here, I should have 5 amps that come back. So hopefully we can see that intuitively, that should be the way that this works out. And so the junction rule states that the current coming in, so we'll call this I total, the total current equals the sum of the current coming out. So I2, actually we'll call that I1 because it's the first branch, and we'll call this I2. All right? And then this coming back out should be our total current, but we'll verify that. Okay, so we come over here to the junction, and we're going to start with junction 1. So we'll call this junction 1. 1. So junction 1. Well, my total current coming in is I total. And that's going to equal the total current coming out. I1 plus I2. Now, down here, I should have I1 and I2 coming in. I1, I2. So that will be on this side, I1 plus I2. That's the sum of the electrical current flowing in equals the current coming out. And that should be equal to the total current because, well, they're the same thing. Now, this is for a parallel circuit. Now, I think that if we were to look at a series circuit, well, we would notice that there is no junctions. And so if there are no junctions, all right, well then the current through resistor 1 and the current through resistor 2 should equal, or better equal, following this rule, the total current. So parallel and series have a different relationship here, and that is that a series circuit, because there are no junctions, series have, objects in series have the same current flowing through. So I1 equals I2. So the current in my first resistor here equals the current in my second resistor. Now in parallel, well, the total current, and this equals the total current from the battery. In parallel, the total current equals I1 plus I2, plus all my other branches. So this is how current behaves in a series and parallel circuits. If you notice, they are the opposite of the voltages. Now, this relationship is very generic, and it only applies to strictly parallel and strictly series circuits. You have to apply it multiple times and in multiple different ways for each different configuration. But for the scope of this class, this should be sufficient.